Thermal expansion is the first of our heat videos. Now, thermal expansion is really, really, really easy to understand. So, when things get hot, they expand. Now, you're not really going to see it too much when you boil your hot water because it expands a little bit. But it does expand a little bit. We're going to show you a video on that in a minute. A thermometer also works on expansion. The liquid inside the thermometer expands, it gets bigger, and it expands in its volume, and it has nowhere to go but up in this empty space here. So when it expands, it moves up the column, and then you can read your temperature. And one of the things we are going to do is we are going to make our own thermometers to measure temperature. On Haiku, there is a YouTube video that I want you to watch. So pause the movie right now because this is important, and go watch that video. It's only 2 minutes, so or it's 2:30. Go watch that and then come back. So in 2007, the Expo train trellis, the Union Pacific train trellis, caught on fire. And one of the images that kept coming up was this one. And do you see this part of the train track where it was buckled? Do you see that? Okay, so one of the things that some of the people were saying was, oh, this was a terrorist attack, and blah, 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 because see, there's an explosion. And I said, no, you need a physics teacher on hand, because here's what happened. You had that long train track, and it was nice and straight, but then it got really hot, because you saw from the video how they called it hell on earth. So you saw how hot this was, and so what happened is the train's tracks expanded, but they didn't have anywhere to go. So they pushed on itself until this area here finally just buckled. So this area here just went boink and popped up. And that's what happens when something expands, but it has nowhere to go. Now, a really, really interesting thing about this fire is that less than a month later, they had rebuilt this entire quarter-mile trestle. You know, it burned down, they demolished it, they took it down. Less than a month later, it was back in operation. Amazing. So how do we do calculations with thermal expansion? It's really not that hard. And there's a nice, simple equation to use this. Is that the length it becomes, or the change in length, it's really a change in length, is equal to your original length, L naught, L original, times, this alpha thing, times the change in temperature. So by how much it changed. So this is our change in length. And the beautiful thing is, it doesn't matter what units this is in. And this is our original length. This is called the coefficient of linear expansion. Okay. I'm going to show you a table. You do not, just like densities and other things, these are not numbers you need to memorize. These are numbers that would be given to you on the test. And this is your change in temperature. Okay, change in temperature is in degrees Celsius, or it could be kelvins, because a change in 1 degree Celsius is the same thing as a change in 1 degree Kelvin. We should know that to get your kelvins, you take your degrees Celsius and you add 273. Now, there is another form of this equation that you need to know if you are in honors physics, but if In regular physics, you just need to know the length version. Honors physics, you need to know that the change in volume is equal to your original volume times beta. Instead of alpha, it's beta times the change in temperature. So you see the equation is basically the same format, just the beta is the coefficient of volumetric expansion. So it's a how does the volume change rather than just the length change. And there is actually a relationship between our alpha and our beta, which we explore in the next video if you're in honors physics. So you can see that our coefficients of expansion for aluminum, it's 25 times 10 to the minus 6. And notice most of these are times 10 to the minus 6. And yeah, they're in engineering notation. That's why they're all 10 to the minus 6, even though it's like quarts here is 0.4 times 10 to the minus 6. So basically what is true is that the larger the coefficient of expansion, the more it expands. Because it's basically a proportionality constant. That's all it is. And so which of these materials do you think expands the most when you heat it up? If we look carefully, ice does. Now, isn't that interesting? Ice expands the most. It's got the largest coefficient of expansion. But which one expands the least? Yeah, it's the quartz. See how it's 0.4 times 10 to the minus 6? So it's a pretty small number. Now, this is the reason, remember we looked at the pot at the beginning. Do you actually see this? No, you don't actually see this. But, you know, when we have our sidewalks, when we make sidewalks, okay, when you make a sidewalk, you have a bunch of squares, basically. There's lines in the sidewalk. And the cracks in the sidewalk basically allow the sidewalk to expand a little bit, because it's only going to expand a little bit when it gets hot. But if you don't have those cracks, what will happen is the sidewalk itself will expand, and you can see it's pushing into neighboring pieces of sidewalk. And if these gaps aren't there, then what happens is it causes our sidewalk to crack. Step on a crack, break your mother's back. So once again, we have our equation. Our change in length is equal to our original length times our coefficient of expansion times our change in temperature. And this is the equation we're going to use to do our worksheet. And it's going to be really easy. You'll finish it in like 10 minutes. The only thing that has to happen is these units need to agree with each other, because the units for alpha are just per degrees Celsius. So it's like degrees Celsius to the minus 1. And our temperature is in degrees Celsius. So you can see that those guys will cancel each other out. And so as long as our length units match each other, we're okay. And we don't have to make our centimeters meters. We don't have to make our inches meters. We can actually work in inches. But if we have inches and feet in the same problem, they need to be the same unit. If we have meters and centimeters in the same problem, they need to be the same unit. So we will do this tomorrow while we are making our thermometers, and you will have so much fun. And so we will see you later. Good luck.